Hello everyone, and welcome to this OpenFOAM programming course here at Flowthermolab. It brings me great pleasure to introduce you to this course. I hope for those of you who are taking this course, you find it very useful, very informative, and it helps elevate not only your OpenFOAM skills, but your programming skills, and that from this you can really start to bring your OpenFOAM knowledge to the next level, start developing your own custom pieces of code or perhaps boundary conditions, or even taking it that one step further and developing your own solvers. So I want to break down this course and introduce some of the main content involved. And the first part of this course is a mini-series on learning some basics of C++. So some of you may have absolutely no experience coding in C++, which I want to really stress from the get-go is absolutely fine. As such, we'll go through some basic concepts. So, for example, this might be creating our very first Hello World program, to looking at concepts such as variables, statements, functions, and what these are. And then we'll progress on to some more complex, perhaps, concepts such as namespaces, data structures, pointers, for examples. I think it is also worth noting that alongside this, as part of Flowthermolab, we do offer a standalone C++ programming course. It's not necessary to take that course before starting this course, but if you do find that you are really interested in C++ programming, or you want to take some of these concepts that we develop at the end of this OpenFOAM programming course that little bit much more further and have a much deeper dive into what some of these concepts actually mean, then I would recommend you to check out this C++ programming course here at Flowthermolab. But next, in the OpenFOAM course, we're going to break this down into, I guess, a set of basic, intermediate, and advanced programming concepts. And these are going to increase in complexity, both in terms of what we do in OpenFOAM and in terms of what we're doing with the C++ code. Obviously, in such a course, we can't cover absolutely everything in OpenFOAM. I think to date, there's something crazy like over 1.5 million lines of code in OpenFOAM. So that would be truly a lot of stuff to go through and be able to capture everything. So I really hope to give you enough information and enough of an idea about key concepts in OpenFOAM, such that if you do come across something new, you will have the right tools to be able to understand what's going on and dig a bit deeper and figure out what that code is doing. So we'll start off with understanding the code in OpenFOAM. So how do we start to navigate what's actually going on in OpenFOAM, looking at the different folders that we see in kind of the SRC folder of our OpenFOAM compilation. We'll do a very easy Hello World tutorial, much like you would do for any programming course. Next, moving on to concepts such as input and output, understanding how the mesh works in OpenFOAM, learning about basic field operations, so how can we manipulate our pressure and velocity fields, for example. And finally, within this section, we'll introduce the concept of debugging within OpenFOAM, and how we can actually really use all of the tools available to us to develop our code. Moving on to some intermediate concepts, we'll be going through the concepts of custom classes within OpenFOAM, which I think is really at the core of most of the OpenFOAM code. So understanding how we can develop our own custom classes, but also how we can begin to understand and set up derived classes and what they actually mean within OpenFOAM. We'll look at how to set up our own libraries such that we could modularize our code and perhaps reuse proportions of codes or functions throughout multiple sections of our code or OpenFOAM in general. And finally, within this chapter, we'll look at custom boundary conditions and how we can start implementing our own boundary conditions within OpenFOAM. Within the advanced section, we'll look at some more challenging concepts, such as how can we modify the transport equation and solve the convective and diffuse terms for a passive scalar transport, for example. We'll also be looking at how we can start to implement the fundamentals of the simple algorithm and applying it to one of our problems. And I think in this tutorial, you'll start to really appreciate how complex something like the simple foam solver in OpenFOAM actually is, even though it's been highly optimized and the number of lines for this code might appear quite small. There's actually quite a lot of things that do go on in the background. And we'll close out the course by looking at 3 practical examples and going through the creation of some custom solvers to highlight how we could come up with something quite simple, or on the complete opposite end, how we can develop much more complex solvers and the whole process that we might go through in OpenFOAM. So for example, on the more simple end, this could be something like a basic solver where we modify the field operations for fun to produce a pressure field that's based on a sinusoidal function of the frequency, inverse distance of your cell center from the center of the domain, and then something like time. And that might result in a nice fun animation like we see in this video here. Or on the much more complex side, we could do something quite advanced where we come up with a new solver. This is capable of coupling DPM, so discrete phase modeling, Lagrangian particle tracking approach, with a Eulerian thin film model, so ETFM. And within this solver, we're going to introduce capability for tracking Lagrangian spray injections to capture things like secondary breakup of droplets injected under a high velocity crossflow. We're going to be looking at introducing further complexities such as new submodels that haven't been implemented in OpenFOAM before, such as a new droplet diameter distribution for our spray injection based on a log Rosin-Ramler distribution, or a completely new film stripping criteria built from scratch, or a complex edge separation criteria which allows for a proportion of the film to separate from the surface as droplets, whilst a proportion of the film remains attached to the wall. And the key thing with developing a solver like this is it's not understanding the equations that are going on in the background of how we solve for that stripping criteria or edge separation criteria. It's really showing you about how we can take something from scratch or a solver that already exists in OpenFOAM, identify what is actually available to us and what we can customize within this solver and the submodels that are present to us, how we can leverage that to our advantage and come up with something new that is there to solve our problem that we develop, and that you can expand upon that and perhaps start to validate that piece of code that you developed against something in literature, so that you can actually come up with a publication for this, and then that can be the grounds for your solver that you've developed that you might then take on for further applications within industry or your PhD or something like that. So throughout this course, we'll have a series of videos that we'll go through to cover all of this material. And at any point, if you have any questions during the course, you can ask in the discussion forum online, where a Flowthermolab instructor will be able to help you, or perhaps even your fellow course members can help you and join in on the discussion as well. And of course, it's only natural that at some point in this series you may struggle with some of the code or concepts within OpenFOAM. And I really do encourage you to use all of the resources available to you and not just skip over something because you don't understand it. So I want to briefly go into the course requirements, and I want to start off by saying that I truly believe this is a course for anyone, whether you have absolutely no coding experience, perhaps you've only just started out in OpenFOAM and you want to learn what's under the hood, or perhaps you have a lot of experience in C++ and have no idea how the OpenFOAM code is structured, or similarly, perhaps you're really experienced in OpenFOAM, but you want to take your skills to the next level to start developing your own custom pieces of code or solvers. So now on to what I think are, I'd say, some soft recommendations for this course. So to begin with, the basics of Linux. So in other words, I think you should be comfortable in navigating around the terminal, CDing into a case, for example, and running your solver, that type of thing. Ideally, I think you should have some existing knowledge of OpenFOAM. Ideally, if you're trying to get started in programming OpenFOAM, you probably have the idea of how to run a case, go through a tutorial file, understand basic error messages, such as if you're missing something in your control dict or FV solutions. You should probably be at a point where if you're thinking about programming in OpenFOAM, then you've already picked up some experience in OpenFOAM. That's not to say you could do the course with absolutely zero OpenFOAM experience. That's definitely possible with how the course is structured. I'm just not sure that if you'd fully appreciate everything we're doing if you have no OpenFOAM experience. Similarly, ParaView, we'll be using ParaView every so often throughout the course, but nothing very complicated, pretty much just opening and viewing our results. So on to the big question that I think will be on a lot of your minds is, do I need to have any prior coding experience, or more specifically C++ experience? Honestly, I don't think you need to know any C++ to get good results out of this course. I think for a lot of you out there, you probably have, and you probably don't realize it, you probably have some level of coding experience, even if it is a very basic level. So for most of you, within maths, when we learn about algebra and equations and stuff, that's a form of programming. And perhaps within university, you did some very small MATLAB or Python projects as part of those university courses, or perhaps you did absolutely none of that. But the way this course is structured is that we'll go through some of the more fundamental concepts of coding in C++ as this kind of standalone mini-series to OpenFOAM. And this will equip us with some basic knowledge of how to set up and create our own applications, looking at the basics from running our very first Hello World program to understanding, what variables are, statements, functions, and then tackling some more slightly more challenging concepts. I will admit we don't get into some very advanced concepts that do crop up in OpenFOAM, such as perhaps inheritance or polymorphism, but we go through this as best as we can whenever it crops up in the OpenFOAM code. And some of you out there will already have plenty of C++ or coding experience, and that's great. Hopefully you'll whiz through that mini-series in C++ and not find it too boring. And equally, for those of you who are still yearning for more or really enjoy the C++ mini-series, and you find out later down the line that in OpenFOAM you do really want to develop some more advanced C++ concepts inside your OpenFOAM code, we do have that standalone dedicated C++ course here at Flowthermolab, which, if you're interested, please do go and check it out. Finally, I think before coming into this course, you should have some goals in mind of what you want to get out of this course, and equally be realistic with them. So some of you may just be curious about coding in OpenFOAM or how it works in the background. Perhaps you want to develop a new boundary condition, or perhaps start building your own solver. And that's perfect. You might find some sections of this course more challenging than other sections, but that's all right. That's only natural. And some of you may come into this course expecting, a very detailed solution to a very specific problem in OpenFOAM. And I think you will struggle with that sort of mindset. This course is about teaching you the fundamentals of building up your confidence in coding within OpenFOAM. So for example, if you were to Google online about coding a specific example, a lot of material that you'll find expects you to be kind of this master C++ programmer, knowing everything and be able to implement the code very easily. Whereas here, this OpenFOAM programming course is all about equipping you with the correct set of tools such that you can go off and start tackling your own problems and coming up with these awesome solutions and pieces of code. And remember, sometimes, programming is a long process. And after all, look how long it's taken for OpenFOAM to be developed. And today it's still being developed and improving continuously over time. So I think it's worth talking a bit about commercial versus open source CFD. So commercial CFD tools out there are quite attractive. They're already pre-packaged. They have all of the solvers that you want in them. You open them up and you can run something, and you can be quite confident with the solution that you're going to get out of them. But the problem is that through doing that, you end up treating them like a black box. The source code is completely closed off. You can have small amounts of customization, i.e. through UDFs, in Fluent, JavaScripting, in StartCCM, but that's quite limited. You don't really have much control over the code. It's difficult to explore why something is not working, and you can't really start modifying a section of code to give you more information and figure out why something is not going as intended, or perhaps you want to modify a certain constant hidden well in the code. But they are reliable. They've been developed by industry experts, they've been rigorously tested, and they work, which is something that needs to be recognized when compared to open source solvers, where, and I'll get onto that point in a little bit, but the source code is completely accessible, meaning that you can customize anything you want, but that doesn't always mean that it's a good idea. So, just because I can go ahead and modify something in the OpenFOAM code doesn't necessarily mean that it's correct. So it's always important to validate what we're doing, and if we have literature available to us online or experimental data to validate against, we should always be striving to achieve what's best and backing up the code that we are developing. And often the big advantage with OpenCFD tools, and specifically OpenFOAM, is that there's large communities with lots of help available, and if you do have difficulties implementing certain sections of your code, chances are if you post online, someone's probably done something similar to that before and can help you out. But I guess more specifically, why choose OpenFOAM as the kind of open source CFD tool to start coding in? And I'm sure if you're interested in this course, you probably know that OpenFOAM is an open source computational fluid dynamics software package, provides a comprehensive set of tools for simulating and analyzing fluid flow, heat transfer, and other phenomena using numerical methods. So OpenFOAM, as we said, it's open source, which means that the software is freely available to users to study, modify, and even distribute as well. And this openness promotes collaboration, innovation, and customization within the community. So it's written in C++ primarily, and that utilizes kind of this modular architecture, allowing users to easily customize and extend its capabilities in kind of this building block style of coding, which makes it well suited for, research purposes, communities online where users may need to implement specialized models or algorithms, and they can be easily slotted into the existing code. And, equally, you can share those online with people and they can compile that custom code very easily. So much like commercial solvers out there, OpenFOAM comes with a wide range of pre-built high quality solvers and utilities for simulating various fluid flow and heat transfer problems. And these solvers, over time, they've been rigorously tested and validated, providing reliable results for many engineering applications. But the key thing is having direct access to these solvers and their underlying code means that we know exactly what is going on. And if we do wish to implement or modify parts of the code, we can do it. And sometimes this can be super easy, or it can actually end up being quite complicated. I think one thing that is touched on quite a lot with OpenFOAM is obviously it's free, and being open source, OpenFOAM is free to use, which can be, quite powerful for individuals, academics, and small businesses with limited budgets. And this also eliminates the need for expensive licensing fees associated with commercial CFD softwares, so we don't need to pay for any additional licensing when we parallelize our code and scale up our simulations, like with other commercial solvers. So as I've touched on previously, there's a lot of community support for OpenFOAM. It has a large and active user community, providing access to forums, mailing lists, online resources for support and collaboration. And, we can all benefit from the experiences, tips, and solutions to these problems that we can, gather from this community support. I think one thing I like about OpenFOAM is that it actually enhances learning. So it can serve as kind of an educational tool for learning about CFD principles, numerical methods, programming techniques that you don't necessarily get from commercial CFD tools. So because we have access to that source code, it's accessible to anyone. So for example, to students, and based on that, you can understand and take your time to learn and dig into that code and figure out how things are working and how different parts of that CFD solver is interacting with different parts of OpenFOAM libraries. And then we can expand on that and develop these principles even further by developing your own solvers or custom pieces of code. And in doing so, you actually learn quite a lot, I think. So it's really powerful learning how to code in OpenFOAM. And as I've touched on, for users with programming skills in C++ and those who understand perhaps numerical methods or even just basic concepts in OpenFOAM, we have the opportunity to develop and implement custom solvers, boundary conditions, turbulence models, other features such as post-processing, function objects, that sort of thing. And this level of control allows us to customize simulations to specific requirements or research objectives, for example. I think there's always a slight confusing thing of which version of OpenFOAM do you choose, especially when it comes to thinking about programming in OpenFOAM. And there are, I guess, 3 main branches of forks of OpenFOAM that are released as free and open source under the GNU, General Public License. So I think to begin with, we have the OpenFOAM variant by Ph.D, which is part of the ESI group, and this has developed and distributed OpenFOAM since I think 2005, and they currently hold the OpenFOAM trademark. And normally we get about 2 release versions, typically every year in June and December. I think the ESI version is quite popular among a lot of the community. It's something that people come across the first time when they look at OpenFOAM, and it's typically what people get involved with first. But we do also have the OpenFOAM variant by the OpenFOAM Foundation, and kind of the main figure behind this development is Dr. Henry Weller, who's, I guess, considered by many as the creator of foam. He still actually develops code for OpenFOAM and was essentially one of the founders of the OpenCFD company in 2004, but then left it to found CFD Direct in 2014. And the last one is Foam Extend, and I think this is a very interesting one, it's developed by Professor Hervé Jassac, who is one of the pioneering developers of OpenFOAM since I think around 2004. And the last release of Foam Extend, which was number 5 at the time of this video, was back in 2022, I think. And we do get some updates every so often. But it's important to note that, this is a lot less popular than perhaps the 2 main forks of OpenFOAM. So I guess the question becomes is which one to choose, especially when it comes to coding in OpenFOAM, because there can be some small differences, but actually it can have quite a strong knock-on effects down the line. And I do think most people choose between the ESI or Foundation version of OpenFOAM, and normally their preference comes down to whichever version of OpenFOAM you adopted first. There can be some differences between the 2 of these, but it really depends on what you're trying to solve in OpenFOAM. And I think in general, most people would prefer the ESI variant over the OpenFOAM, over the Foundation variant. And I think sometimes, the ESI gets it slightly better than the Foundation version, even though fundamentally the majority of the code is exactly the same. The Foam Extend version can be quite interesting to look at, because there are certain things that are unique to this version. So, for example, it actually has a fully working coupled solver for pressure velocity coupling instead of using a segregated approach, which is really interesting. But you need to be careful because it can fall quite behind in developments versus the other 2 forks, and may lack improvements that we see in the latest version of, say, the ESI build. And as such, the source code can end up being quite different in certain areas and quite confusing to compare if you have them side by side. In this course, we'll be using the ESI version of OpenFOAM, and for the most part, the code that you develop in the ESI branch would work perfectly fine in the Foundation branch of OpenFOAM, but there are quite a few times where you might actually need to tweak a class declaration, for example, to get it working in one branch to the next. So I would avoid swapping and changing between OpenFOAM branches. Look at what you're developing and what your requirements are. Have a dig around in the code and really choose one of the branches and kind of make a commitment to staying with that branch. And if you do need to, and you find out that one branch has something in it that your current branch doesn't, you can go and swap to it, but you may need to think about how that might affect the code that you've developed so far. So I guess the other question is why is C++ used in OpenFOAM? And C++ is actually a really powerful and widely used programming language known for its efficiency, performance, and flexibility. So for example, in terms of efficiency, C++ allows for low-level memory management and optimization, which can result in highly efficient code execution. And this makes it suitable for developing high-performance applications like a computational fluid dynamics solver like OpenFOAM, where if you think about our mesh and the fields that we're solving, we actually have a huge amount of data that's stored in memory, especially if your cell counts go up to millions or hundreds of million cells. So having something really efficient like C++ really helps improve the performance of our CFD solvers. So talking about performance, it also offers direct access to hardware resources and supports features like inline functions, compile time optimization, and that enables developers and us to write code that runs quickly and efficiently. C++, as we talked about at the start, it's really flexible. It supports both procedural and object-oriented programming styles, and this flexibility allows developers to choose the most appropriate programming style for their specific needs. And then finally, portability. C++ code can be compiled to run on various platforms and architectures, making it suitable for developing cross-platform as well. So I know we've touched on it, but why use C++ in OpenFOAM? And OpenFOAM's choice of C++ as the primary programming language is for several reasons. So computational fluid dynamics simulations involve quite complex mathematical computations and large data sets. And because of C++'s efficiency and performance, it's well suited for handling those computational tasks, resulting in faster and more accurate simulations. So for example, you wouldn't have the same performance if you were writing your CFD solver in Python instead of C++. It provides control over memory management, data structures, allowing us to optimize our code for specific cases and performance requirements. And it integrates well with existing numerical libraries and computational frameworks, which allows the development of some quite robust and scalable CFD solvers when we start thinking about parallelization as well. And OpenFOAM's modular architecture leverages C++'s features to facilitate easy customization and extension of the code, which we'll see as we start going through this course. And we can implement new models, algorithms, solvers, or different components really easily in the grand scheme of things by writing C++ code and kind of just slotting that in and integrating them into the existing framework without really having to have too much of a concern that we're breaking the rest of the code, that sort of thing. And I think the last question, and we covered this at the start, do I need to learn C++ to be able to code in OpenFOAM? And technically, no. If you wish to just change something simple like a constant value in some piece of code, then obviously no. Perhaps maybe you want to just modify the constants in a boundary condition. That's quite basic stuff. It doesn't require you to understand C++. You just have to open up a text editor, change some values, and recompile the code, much like you would when you install OpenFOAM for the first time. However, understanding C++ allows us to really dig in and figure out what's going on in the OpenFOAM code. It's what allows us to be able to customize and extend OpenFOAM to suit our specific needs in terms of research applications, engineering applications. And through understanding C++, we can figure out why certain things are done in OpenFOAM. And that means that when we come to introduce new things like solvers, boundary conditions, turbulent models, post-processing utilities, we know why things are done in a certain way, and we can follow that structure and be confident that actually our code is working to the best of its abilities. So learning C++ becomes a valuable skill for us when using OpenFOAM. And, equally, by developing code in OpenFOAM, you start to naturally learn C++ as we start to understand how that code is structured and why it is implemented in a certain way. So learning C++, can be quite a daunting experience, but hopefully throughout this course, you'll start to pick up on some of those core concepts through that initial mini-series. And then when we start introducing that into OpenFOAM, it will start to make a lot more sense, and we'll start to develop that core knowledge even further.